Welcome. In this video, we are going to take a look at some conjugate acid-base pairs, and we're going to be looking at the Bronsted-Lowry definition of acids and bases, and look at how we can interpret these Bronsted-Lowry equations and identify things that are conjugate acid-base pairs. So first, we're going to take a look at some of these reactions that are already written out for us, and just get practice identifying which things are acids or bases. So just a quick review of the Bronsted-Lowry definition. According to this definition, an acid is a substance which is a hydrogen ion donor. We often refer to that hydrogen ion as a proton. So we say acids are proton donors. And then a base is something that is a hydrogen ion acceptor. So it is a proton acceptor or a proton taker. So whenever you're looking at this type of reaction, how we identify this as a Bronsted-Lowry reaction is if we take a look at this equation right here, we notice that what's happened, if you compare the reactants and the products, is that a hydrogen is moving from one molecule to another one, from one species to another. So in this case, it looks like what's happening here is that the HNO3 is giving a hydrogen to the water. Because you see how afterwards the HNO3 has now lost its hydrogen and the water has gained one? So since the HNO3 is giving a hydrogen to water, we see that, HNO3 is acting as the acid. So HNO3 is our hydrogen donor. And the substance that is left behind after it donates a hydrogen is known as the conjugate base. So NO3 minus is the conjugate base of our acid HNO3. Now, if we look down at this one, we are looking for, in this problem, we're trying to identify what is our acid. So our acid is our hydrogen donor. So I want to look for a substance that gives up a hydrogen. So it looks like in this example that the H2S is giving up a hydrogen. It is giving it to the H2PO4. So H2S is our acid. What's left behind after it gives up a hydrogen, we call that the conjugate base. So HS minus is the conjugate base. Down here, who's my hydrogen giver? It looks like HF is my hydrogen giver. It is going to give a hydrogen to water. And then what's left behind after it gives that hydrogen is F minus. That is the conjugate base. Down, do just a couple more here. Again, I'm trying to identify my acid. My acid is my hydrogen giver, my hydrogen donor. All right, so in this case, it looks like NH4 gives up a hydrogen to the Cn minus. And I can tell that because if I compare before and after, I go from having 4 hydrogens to now I only have 3 hydrogens. That's what I mean by saying it has given up one of its hydrogen. What's left behind is known as the conjugate base. And then last one, it looks like in this case, our hydrogen giver is water. Water is behaving as an acid in this case, and the conjugate base of water is OH minus. Something I want to throw in at this point, which we will come back to this idea later, is that when you're talking about these conjugate acid-base pairs, the conjugate of a weak acid is going to be a weak base. So we sometimes say weak pairs with weak. So what we mean here, like HF right here, this hydrofluoric acid, this is a weak acid. I know it's a weak acid because I've memorized the 6 strong acids, and if it's not one of your 6 strong acids, that means it must be a weak acid. So HF must be a weak acid. It's not one of my strong ones. Therefore, F minus, its conjugate, is a weak base. Same thing over here. H2S is a weak acid. I know it's weak because it's not one of my 6 strong acids. So the conjugate of that weak acid is what we call a weak base. The other rule is, so weak pairs with weak. What if it's strong? Well, if you have a strong acid or a strong base, then the rule is strong pairs with neutral. So the conjugate of something that is strong is going to be neutral. So we actually see an example of this right here. Water is neutral, and the conjugate base of water is, well, basically the strongest base you can get. It's just pure hydroxide. All right, so this is a strong base. Its conjugate is neutral. A weak base, its conjugate is going to be a weak acid. So that's just a good rule to keep in mind that I thought I would bring up here since we're looking at some pairs. Okay, now let's take a look at some other examples. So we want to identify both conjugate acid-base pairs in this set of problems right here. All right, so I'm going to label both conjugate acid-base pairs. So it looks like what happens here in this example, it looks like NH3 is behaving as the base. It's accepting a hydrogen. Water is behaving as the acid. And as that's on the reactant side. And if I'm trying to look at my conjugate acid-base pairs, NH3 is the base. Its conjugate acid would be the thing that it makes after it takes that hydrogen. So NH3 is the base, NH4 plus is its conjugate acid. H2O is being the hydrogen giver in this scenario, so water is behaving as an acid, and then OH minus is its conjugate base. So I'm always going to have two conjugate acid-base pairs in this type of reaction. Let's look at this next one down here. Looks like in this case that HCN is being the hydrogen giver. So HCN is the acid. In this case, water is acting as the base. So HCN is my acid. What's left behind after it loses that hydrogen is the conjugate base. So CN minus is the conjugate base. Water in this case is behaving as the base, and then its conjugate acid is H3O plus. And I want to point out again what I said earlier, weak pairs with weak, strong pairs with neutral. So NH3 is a weak base, its conjugate acid is a weak acid. HCN is a weak acid, its conjugate is going to be a weak base. Over here though, water is neutral, its conjugate is going to be strong. And down here, water is neutral, so its conjugate acid is also going to be a strong acid. So weak pairs with weak, strong pairs with neutral. All right, and then one more down here. It looks like in this case, NH4 was being the hydrogen giver. So NH4 is my acid, NH3 is its conjugate base, and then CO3 2 minus was acting as a base, and then HCO3 minus is its conjugate acid. So writing the formula for the conjugate bases for the following acids, all I'm going to do is I'm going to remove a hydrogen. So when you do this, on the one hand, it's really easy, just take a hydrogen away. But the one thing you want to be careful with is charge. So whenever you remove a hydrogen, you're removing a positive charge. So neutral things become a negative 1. So like H2SO4 becomes just HSO4. HF becomes F, and these all have negative 1 charges. HC2H3O2, I'm going to remove 1 hydrogen and make C2H3O2. Boom. And then over here, these ones, these are substances that already started out as having a charge. Like H2PO4 minus becomes HPO4 now with a negative 2 charge. Because it already started out negative and then it lost another positive thing, so now it's got a negative 2 charge. NH4 starts out positive, so when it loses a positive, it becomes neutral. So be careful with charge on these ones. Now let's do the same thing, but write conjugate acids. So for these ones, you're going to add a hydrogen instead of take it away. So NH3 becomes NH4, and I add a positive charge. This becomes, looks like that. Or feel free to, if you put H6 instead, that's totally fine. CO3 2 minus becomes HCO3 with a 1 minus charge. And then HPO4 becomes H2PO4 with a 1 minus charge. So be careful with the charges when you're writing these conjugates. And then let's try and fill in some of the blanks ourselves here. So we want to identify, figure out our acids and bases and what the products would be. So this case, it is an anion, SO4 minus. It's an anion, negative ion. Anions tend to be bases. They are negative. They tend to attract positive charge. They tend to be good hydrogen takers. So SO4 is a base. So it is going to take 1 hydrogen. We only ever move 1 hydrogen at a time in this scenario. And so that will form HSO4 and OH minus. So my SO4 minus, it is a base, it's being the hydrogen taker. Water is behaving as an acid. And then let's identify the conjugate pair. So this is 1 conjugate pair, and then this is 1 conjugate pair right here. All right, how about this one, HCN? Whenever you have a substance that starts with an H like this, it often tends to be an acid. So it's going to be a hydrogen giver. So it will make CN minus and H3O plus. And these are our conjugate pairs, HCN and CN minus, and then H2O and H3O plus. Last one, NH3. This is an example of an amine. So it's a molecule containing nitrogen. Amines tend to be weak bases because those nitrogens are very electronegative. And we talk about this in the acid-base reading, kind of summarizing how you could recognize something as being an acid or base. So it's going to be a base. So it is going to be a hydrogen taker. So NH3 becomes NH4, H2O becomes OH minus, and here are our conjugate pairs. So this one right here, and then this pair right here. All right, which of these are conjugate acid-base pairs? To be a conjugate acid-base pair, you have to differ by just one hydrogen. That's it. So A is tempting. They almost look like a pair, but no, they're not a conjugate pair because they're two hydrogens different from each other. Okay. B is a acid-base pair. The only difference there is one hydrogen. C is, sorry, I kind of crossed that out there. Boom. C is not. They look similar, but they differ by their anion, not their hydrogens there. And then D, those look similar, but they differ by their number of oxygen atoms, not by their number of hydrogens. So you can identify a conjugate acid-base pair because they differ by just one hydrogen ion. All right, and then one other type of question you might see that's related to these Bronsted-Lowry equations would be something like this. So notice how I've got a generic equation, and I can identify, I can take a look at this and see who's my acid and who's my base. So it looks as though my HX is being the acid. It is giving a hydrogen to Y minus, right? So it looks like HX is the acid and Y is the base. Therefore, we can identify the conjugates. So HY is the conjugate acid, and then X minus is the conjugate base. So I've got two conjugate acid-base pairs. Let me separate those out. Okay, now let's read the question. Question is, which species is the strongest acid? So we've got two acids here. We've got HY and we've got HX. Which is the strongest acid? Justify your reasoning. Well, what do we know about this? Well, we know the K for this reaction is greater than 1. So that tells us that the forward reaction is favorable, right? So K is greater than 1. That means it is favorable. That means that forward reaction is going to, proceed. You're going to end up with more products than reactants. And it looks like in the forward reaction, the substance that is acting as the hydrogen giver is my HX. So since the forward reaction is favorable, that tells me that the acid, which is the acid in the forward reaction, must be the one that's better at being an acid, right? That is my stronger acid. So it looks like HX in this case is my stronger acid. If K had been less than 1, let's imagine this scenario. What if K had been less than 1? That would tell me that the reverse reaction was more favorable. Okay. So, and in the reverse reaction, that would be going this direction. My acid would be HY. So if K was less than 1, that would tell me that the reverse reaction is favorable and HY is the better acid. But since my forward reaction is favorable, then that means HX is my stronger acid. So that's a little kind of side problem. You might see a question like that pop up on the AP test. So it's an application of thinking about the magnitude of K and favorability and how that might connect with our, Bronsted-Lowry definitions of acids and bases. Let me know if you have any follow-up questions. Thanks for watching.